Hello, everyone. Welcome to our, in the United States, Valentine's Day live session. We love having you here with us every month. We are happy to be here with you. And my name is Matthew. I am one of the course staff, sort of behind the scenes. We get everything going. And I'm going to hand this over to Chris to welcome everyone, and then I'll go over a couple of the guidelines for the session, and then we'll get started with questions. So Chris, why don't you say hello to everyone and we can get going.
Sure. Welcome everyone. If you're in one of our online classes or if you just found it by some other means, this is the place you can ask any question about astronomy.
Excellent. And for those of you who are new with us today, welcome. Please post your questions in the chat in YouTube, in that browser. I will select them from there, and please only post your questions once. We see every single one of them, and I try to get to as many as I can, but we do jump around a little bit to get a variety of topics and to give lots of people a chance to get their questions answered. And if there's lots of similar questions, just know that I lumped them all together, and that we saw yours and we're not ignoring you. It's just a lot to get through. So thank you for your patience. The very first question today is from one of our live participants. Country Visits asks, gravity waves. How do they work so that different waves from different locations do not interfere with or cancel out the one wave being detected, like waves on a pond distorting each other?
That's a good question. Gravity waves are propagating through the universe from all different sources, primarily cataclysmic events like merging black holes and neutron stars, but also a lower level of sort of stochastic gravity waves from the early universe. These are space-time distortions, and they are additive. So if two gravity waves meet, or they come from different directions and the perturbations overlap, then they just simply is an additive effect, and they pass through each other as if they didn't see anything. So they don't interfere at the level of destroying the signal. They simply work additively, because a gravitational wave is essentially an amplitude of a space-time distortion, and when two or three waves combine, the amplitudes simply combine linearly.
So that's kind of an interesting question. Do you think we'll ever be able to do like gravitational wave interferometry or anything like that, like we do with visible light waves?
I think that the question of interferometry with gravity waves is not going to ever happen. Interferometry is a property of electromagnetic radiation, which has particular quantum properties of diffraction and interference, which allow interferometry to work. Gravitational waves are a property of space-time itself. They're not an explicitly quantum level phenomenon, and so they don't combine or operate in a way as to allow interferometry to operate.
Excellent, thank you very much. The next question is from Adrian Murray, who asks, are red dwarf stars more populous than any other population of stars in the universe?
Yes, red dwarfs are the most abundant type of star. A red dwarf is a cool main sequence star that is a star that, like the sun, is fusing hydrogen into helium as its energy source, but it's much lower mass. And so red dwarfs are stars near the fusion mass limit, which is 8% of the mass of the sun, 0.08 times the mass of the sun. So red dwarfs are sort of in the range from 8% of the mass of the sun up to about a third the mass of the sun. They have cool outer envelopes or photospheres. The sun's photosphere is 5,800 Kelvin, makes it a yellow star. The coolest red dwarfs have outer envelopes that are 3,000, 3,200 Kelvin, which makes them red. And the mass function of stars is such that there are about 100 red dwarfs for every sun-like star.
So that is a good connection. Irina has a question, who's on with us live. And they'd like to know, what is the actual color of the sun? I'm confused. Can you talk a little bit about what the color of our star is?
So the natural color of the sun it's the color indicated by the temperature of the photosphere in a spectrum. So the effective temperature of the sun's photosphere is 5700, roughly 5700 Kelvin. And if you look at that on a spectral chart, it indeed is the yellow color we're familiar with. But the actual color of the sun as observed comes because we see it through an atmosphere. And the atmosphere, of course, has particular properties. And in particular, the small particles in the atmosphere scatter blue light more efficiently than red light. That's why the sky is blue. And they therefore subtract some amount of blue light from any object beyond the atmosphere and therefore make it slightly redder. So the sun as seen from the Earth is slightly redder than it would appear from space.
I think there's also something about sort of the peak in wavelength. People have heard that the peak in wavelength is green. So why isn't the star itself green, even though there's this sort of peak in wavelength?
Right. So the peak wavelength of the sun is determined by Wien's law, which is a just standard law of radiation physics from the 19th century. And yes, if you just take the single wavelength, which is the peak of the blackbody spectrum of the sun, it would match to the green part of the spectrum. But the sun has a broad spectrum, of course. It's a thermal spectrum that spans a significant range of wavelength. And if you add together, all the blue, the red, and different colors of the sun, then the net aggregate color of the sun to the human eye appears yellow.
Excellent. Thank you very much. I think that clears up that question. Ubaid Zaman sent an email. Can you kindly give some idea about dark matter and dark energy? How did we come to know about their existence? And do we have any detection methods or experiments for measuring them in the future?
That's a big question, so I'll give a short-ish answer because it could be a long answer. Dark matter, dark energy are the two enigmatic components of our universe. Dark matter is about 24% of the material universe, holds galaxies together, distorts light seen through the universe. Dark energy is about 2/3 of the universe and contributes to the accelerating expansion. We have very many methods to find dark matter by gravitational lensing, by the motions of objects, even though we can't see it directly because it doesn't emit light. We only have one way really to detect dark energy, and that's through the accelerated expansion of the universe. And then there are some very subtle indirect ways about how dark energy affects the way clusters form and so on. So there's a research agenda, of course, trying to find out what dark matter actually is, since we have a lot of astronomical observations of dark matter. Dark energy, the research agenda is in a much earlier stage because we just have so few handles on detecting dark energy itself, and we really have no idea what it is, and that prospect is still pretty far off. So these are the biggest issues in cosmology, and dozens, probably hundreds of researchers are trying to address them. And we might hope for a breakthrough on dark matter in the next decade. For dark energy, it's hard to tell.
Excellent. Thank you very much. The next question is also from an email. Wendy Traver asks, a recent study revealed thrust faults around the south lunar pole of the moon due to cooling of the core, which is shrinking. But wouldn't all bodies in the solar system be cooling as time elapses since the Big Bang, and thus be subject to shrinking and thrust faults?
Yes, all massive objects in the solar system are cooling. And remember, even long after their formation in the solar system, 4.5 billion years ago, so well after the Big Bang, they are still cooling after they form because they contain radioactive material in the rock, and that is the heating source, and that radiation gradually leaks off into space. Objects like Saturn and Jupiter are still cooling because they're actually slightly contracting, so they have a small amount of net heat. But yes, rocky object that is still cooling, even if it's a very slight cooling, because the moon has no metallic liquid core, it has no magnetic field, it has no plate tectonics. These are quite subtle seismic shifts or geological activity in the moon, similar to the kind of geological activity we might expect to see on Mars that does not currently have active volcanism. But any object of that kind of size will have some level of seismic activity. The moon is a near enough object that we can study directly, And so we can see much more subtle seismic activity than we could on any other astronomical body.
The next question is from Neha, who asks, one of the aims of science these days is to look for extraterrestrial life. How would this be beneficial for humanity?
It's not clear there's a direct benefit to humanity in looking for life beyond Earth, unless, of course, the life is near enough by and we can study in enough detail to learn how it works in ways that might help us improve biology or improve the ability to fight diseases or cure genetic conditions. We have our own approaches to that, just using terrestrial medicine, but if we found alternative biology in a different framing of it, that could provide insights into how organisms work and how genetics works. But that's a kind of long shot. I think really there's no obvious direct benefit from life beyond Earth on the terrestrial scene. It's just a situation where we learn our place in the universe a little better, and we learn whether or not we're alone.
The next question is, we had two sort of similar related questions. Andrew Wang asks, do amateur astronomers help progress our understanding of the universe today, or is that era long gone?
No, amateur astronomers are very helpful in doing research, and that era is actually getting stronger. It's growing rather than getting weaker. Amateur astronomers have always had excellent telescopes, some of which they build by hand and even grind their own mirrors. And those telescopes can be substantial in size, up to a meter or more in some hands. And they're driven by motors, and they're highly automated, and they're very sophisticated. But the instruments behind the telescopes have improved too, because CCDs have matured to the level where even a cooled CCD with a photoelectric cooler can be had for a few $100s. And so, and infrared instruments are now even appearing in some amateur astronomy hands. So the instrumentation of amateur astronomy is a lot better, and that means they can contribute to many different research projects. And there's even a very small group, much smaller than the optical astronomers, of radio amateur astronomers building their own radio telescopes and antennae to detect radio waves from space. So it's a very active field, and real contributions are being made to research. Amateur astronomers feature on dozens, if not hundreds, of refereed research papers each year.
Excellent, thank you. The next question is from Ayan Khan, and I think the real question comes down to how a mental model of the universe can compare with, or a physical or mental model that we have of the universe can compare with the real sort of mental or the models that astronomers are working with. So we know that our universe is expanding continuously, but is it expanding into something? So like with the example of if we blow blow up a balloon in our atmosphere, then there's something inside, something outside. So what are the limits of these kind of analogies, these expansion analogies, and how does it compare with our real universe?
So analogies and metaphors even, and simple physical models are helpful in understanding our universe, but they really don't ever fully capture the situation. In other words, even the best analogies, which many times you encounter in a teaching situation, are flawed at some level or limited. And it's important to use the analogy and help and learn from it, but also recognize its limitations. And the expanding universe is a good example. The balloon example, blowing up a balloon with dots on it to represent galaxies, is commonly used to teach cosmology. But the huge difference with the real universe is the balloon is expanding. It has an inside and it has an outside that it's expanding into, the air or the room or whatever environment it's in. And the universe is not that way. The expansion of space-time is the totality of the universe. There's nothing outside it, nothing beyond it. And so that analogy is definitely flawed in that sense. The balloon analogy is useful at some level to talk about the isotropic expansion, where every galaxy moves away from every other galaxy. But it's a two-dimensional analogy, and our universe is 3 dimensions of space plus 1 of time. So that's a good example of an analogy that's helpful up to some point and then simply fails to capture the physics of the real universe. And in truth, the real reason that these models and analogies are limited is that the universe is fundamentally described mathematically by general relativity and by the cosmological world model in a mathematical sense. And so physical models and analogies rarely capture the mathematics.
The next question is from Ravi Narasimhan, who sent an email. I've read that the ELT, the Extremely Large Telescope, instruments will perform direct high-resolution spectroscopy of exoplanet atmospheres from the visible to the mid-infrared. If this succeeds, could JWST focus on cosmological problems where being in space presumably still offers some advantage over ground-based telescopes?
Yes, the ELT, the Extremely Large Telescope of the Europeans are busy constructing in Chile, and it's quite advanced. They also have full funding for it, so it probably will take first light by the end of the decade. Is going to be intending to look at exoplanet atmospheres and signs of life, biomarkers in the optical and infrared. It's a huge telescope, of course, far larger than the 6.5 meter James Webb, so it has that advantage. And in the optical, its adaptive optics also give it a very strong advantage because it can make very sharp images, pretty much as sharp as you can make from space. The place where James Webb would retain an advantage is in the infrared, because in the infrared it's not simply a matter of telescope aperture, it's also a matter of the backgrounds, and infrared backgrounds are thousands or more times brighter on ground than they are in space. So James Webb will do better in the infrared because of the low backgrounds. And also James Webb was never really designed to do this exoplanet atmosphere experiment because it was constructed and the spec was written before exoplanets were discovered, whereas the instruments for the ELT are being designed and optimized for this experiment. So in that sense, the ground-based telescope like ELT will probably solve this problem or make far more and better observations of exoplanet atmospheres.
The next question is from Sphere, who is on with us live. Hello, what do you think about the connection between the singularity in black holes and dark matter? And does the singularity in a black hole potentially prove the existence of dark matter?
So there have been a little flurry of research papers, theoretical papers, talking about a potential connection between black holes and singularities within them and dark matter. It's very speculative, and it's not based on confirmed physics, because the truth is we don't know what dark matter is. So that's a big limitation on this kind of theorizing. We also don't really know what happens inside in a black hole. The singularity theorems of Roger Penrose and Stephen Hawking from the 1970s amount to a censorship theorem where we really can't know what's inside the event horizon, and so the nature of the singularity is clouded in mystery. And so I think this is interesting theoretical research, but as far as I've seen, there's no direct observational test of this idea.
Thank you. The next question is from Akshat, who would like to know how can undergraduate students contribute to the field of astronomy and astrophysics?
Undergraduate students, including those at my institution where we have 300 astronomy majors, an enormous number, I think the largest in the country. They are mostly taking classes and working towards their degrees, their Bachelor of Science degrees in physics and astronomy. But many of them are doing research. In our department, a third or more, something up to half of the students do research at some point. So all undergraduates nationwide and worldwide who are studying for degrees in a research-strong department will have opportunity to work with faculty and do research projects. And that is considered a standard thing for our undergraduates. And indeed, the best undergraduates, the ones who go on to graduate school, will not succeed in getting into a good graduate school unless they've done research as undergraduates. So it's pretty much a standard expectation, and those students are contributing to significant research projects. They are not leading the project, of course. They're junior team members, but they will be getting their names on papers. They will be going to conferences. They will be participating in the collaboration. And so there are many undergraduates doing substantial work on research around the country and around the world.
Excellent. The next question is from Andrew, who's on with us live. It's related to an earlier question about amateur astronomers contributing. What's the minimum size for a telescope that can make real scientific discoveries?
It depends a little on the project you're doing, but I think there's some projects where something as small as a 10-inch telescope could make significant contributions, assuming it's equipped with an electronic detector like a CCD, because some of the work of amateur astronomers involves monitoring the brightness of stars, variable stars, and many of those stars are quite bright. I mean, some are even naked eye stars, so they're bright enough the eye could see them. And even the work of transits, looking for exoplanets by their transits, just needs a fair precision. It doesn't need enormous light gathering power because the stars themselves are bright. So there's no particular minimum size, but I gave 10 inches or a foot or a third of a meter, 30 centimeters as a reasonable lower bound to be able to make a contribution to research.
The next question is from Peter Bifus, who sent an email asking, if the universe continues to expand to the point where the lights go out, where does that leave the concept of space-time?
Well, space-time in an accelerating and expanding universe continues to exist. It's stretched out, of course, by the accelerating expansion, and so any deviations from flatness or isotropy of the space-time will be smoothed out like wrinkles on a sheet if you spread the sheet out or stretch it. But space-time itself is not destroyed or does not go away or change its fundamental properties based on accelerating expansion. It's just that the metric of space-time, which is the mathematical description of the geometry, it just has an expansion factor and a growth factor.
Excellent, thank you. The next question is from Lauren Rosenthal, who sent an email asking, what would it mean if we found a new element in a meteor or exoplanet?
A new element, was it?
Yes, correct. Yeah. What would it mean if we found some kind of new element, or we could expand it to even mean a new mineral?
Right. Well, a new element, I'll answer that question because there is a good answer to that question, and it would be a shock and a surprise. We believe that chemistry is universal. We believe that the elements in the periodic table that were pulled together, the understanding of that was pulled together over 100 years in the 19th into the 20th century. We believe that that's all the universe has created and all that's available to observation. And so there is no element that's been seen astronomically in the last half century that does not exist or cannot be produced on the Earth. So we think there's no surprises there as far as seeing a new element, that the physics of that has been established and there should be no surprises. As a side note, I point out that helium was an unusual element because it was the first element to be discovered in space rather than on the Earth. And of course, it's one of the most abundant elements in the universe. As far as minerals, though, certainly there could be surprises because minerals are just chemical composites or chemical, they're combinations of many different kinds of molecules actually in a sort of rocky form. And there's essentially an infinite number of potential minerals, and so we could definitely see mineral forms out in space or in rocky exoplanets that didn't have an equivalent on the Earth.
Our next question is from David Gold, who's on with us live. What method does the James Webb Space Telescope have to detect carbon-based life forms on exoplanets?
The James Webb Space Telescope cannot directly detect life forms on exoplanets because it's simply unable to see an exoplanet in enough detail, that is by making an image of it, to understand whether it contains life. The James Webb is limited, as are many ground-based telescopes, to an indirect experiment where you study through transits or backlighting from the orbiting star the atmosphere of the exoplanet, and you do spectroscopy of that atmosphere. And that allows you to detect all deviations from equilibrium caused by metabolism, such as a photosynthetic organism that respirates oxygen and adds it to an atmosphere. So that's the method that's used. Now, whether that organism, if it's seen, if that biomarker seen in an atmosphere, if that indicates a carbon-based life form, is a statistical probability that it does, because carbon is one of the most abundant elements in the universe, is uniquely able to make long chains and molecules that can store information. So we expect carbon-based chemistry and biochemistry to be universal.
The next question is from Navya, who asks, I would like to know if someday we will ever have any future missions to the nearest exoplanets.
Well, there is a mission, Breakthrough Starshot, that is intending to send a fleet of nanobots, tiny, few-gram spacecraft powered by solar sails to 5% of the speed of light, to go to Proxima Centauri, the nearest star system, which observations have shown has at least one Earth-like planet. So it's a good prospect for biology nearby. So this Breakthrough Starshot project is not fully funded. It had a $100 million investment from Yuri Milner, a Russian billionaire philanthropist, and it has some money from other sources. But they're developing their technologies to be able to beam microwaves into Earth orbit and power the solar sails and accelerate the nanobots to this appropriate speed. There's got to be huge redundancy, because not all the nanobots will get to their target. And so you have to send fleets of them. And it's not clear what the total price tag of this project is, but that's the only current project that could get us potentially to the nearest exoplanet physically with small space probes in less than a century.
The next question is from Hernan Reyes, who asks, I read in a French astronomy magazine that scientists had tried to capture the dimming of Orion's star Beetlejuice caused by a passage of an asteroid, so an asteroid blocking this star. How is it that such a small object, as small as an asteroid, can block such a large star? And how does one prepare and predict for that kind of a transit or of an event?
Yeah, so this is an unusual event, and it's actually really distinct from the kind of transit that we talk about with exoplanets. In the exoplanet sphere or in the solar system, a transit is where a small object crosses the face of a bright object like a star and dims it momentarily. And we can see this in the solar system with Venus and Mercury crossing the face of the sun as seen from the Earth. And in exoplanets, it's the standard method for detecting exoplanets. This occultation of Beetlejuice is a different thing. It's an occultation, for example, not a transit, which means the small rocky body in the solar system is, of course, physically very small, but it's millions, hundreds of millions of times closer than Beetlejuice. And Beetlejuice, although it's a giant star, is seen at such an enormous distance that its angular size is tiny. It's unresolved, essentially, or it's maybe a few arc seconds across. And so the asteroid so clear nearby is fully occulting and blocking out the light. So it's a timing experiment where, as the occultation comes and goes, you hope to diagnose the atmosphere of Beetlejuice when it comes in and out of the occultation. And the fact that it's exciting is because that is quite rare, to have an inner solar system body occult a particularly bright and interesting star. It doesn't happen very often, so people will be definitely trying to gather as much data as they can.
The next question is from Rashmi, who asks, how has astronomy grown over the years? How has it changed since Newton and Einstein, and what future changes do you expect to see?
So the growth of astronomy has been profound since Newton and Einstein. Since Newton, it's been profound because observational astronomy just grew steadily through the 17th and 18th century with larger and larger telescopes, and that continued into the 20th century. So observationally, the growth of astronomy has been fueled by an enormous gain in collecting aperture of our largest telescopes, which have grown from a meter or so up to the 20 and 30 meter telescopes we're building and contemplating now. Theoretically, it's grown because the Newtonian gravity theory was supplanted, if you like, or replaced by Einstein's general relativity in the early 20th century. And 100 years of general relativity have also led not to the theory ever being disproven, but to have enormous verification and many new tests of general relativity, most recently with gravitational waves. So the growth of the field is phenomenal. It's also driven by technology, not just the telescope building technology, but the detector technology that's let us see all parts of the electromagnetic spectrum. Until 100 years ago, there was only optical astronomy, and then radio technology was developed in the 30s and 40s, infrared technology in the 50s and 60s, X-rays, and so on. And so we have an enormous electromagnetic spectrum to work with, and that's the modern astronomy world relies on multi-wavelength observations. So in all those aspects, astronomy is unrecognizably different and more advanced than it was, say, in Newton's time.
The next question is from Carme, who asks, do tachyons exist, and is there a way to use tachyons to travel if they do exist?
Tachyons are hypothetical faster-than-light particles. They appear in some representations of physics as possible physical entities, but there is no observational evidence for them. There are ways you could detect tachyons if they exist, because it's a faster-than-light particle, so it would sort of violate causality in certain kinds of experiments we're familiar with, which are usually bounded by the speed of light. So there are philosophical and logical problems with tachyons. There's no underlying and base and sort of fundamental physical theory to predict them, and there's no observational evidence for them. So I would say all the sort of hypothetical uses you might make of tachyons are just that, hypothetical.
The next question is from Prashant, who asks, how does a white hole affect your body?
Well, if white holes existed, it might affect your body if you were close enough to a white hole, because it's an energy source in principle. It's a place where space-time is connected between two disparate regions of the universe, and energy can flow into one end of the black hole, into a black hole, and out of a white hole that is paired with it. That energy could have all sorts of effects on the body, but we have energy sources in the universe like quasars and active galaxies that already exist. None of them are nearby. So again, there's no evidence that white holes exist at all. They're just theoretical constructs. If they did exist, one would have to be very nearby for it to affect us. So in the levels of worry about harm, I'd say white hole harm worry is one that you put pretty far down the list.
The next question is from Ryan Weber, who asks, as something falls into a black hole, its time slows as it approaches the event horizon. From the perspective of that something, can it be said to ever actually enter the black hole?
Yes, that's one of the interesting features of relativity. It's a conundrum, if you like. I mean, it seems like a paradox, but it's not necessarily. That you have to take two different perspectives. From the perspective of somebody outside the black hole, it is indeed the case that an object falling into the black hole is essentially gravitational redshifted, so the radiation from it is gradually stretched in wavelength to the point where it becomes invisible, because when it's stretched infinitely at the event horizon, the object becomes black. So the object falling into a black hole becomes totally dark at the event horizon, and also its time appears to slow down and its time freezes at the event horizon. As seen by a person or an object falling into a black hole, there is no such distortion, because the clock works normally. The object plunges into the black hole through the event horizon to a completely uncertain fate, because we don't know what happens inside event horizons. So the experience of the clock and the person falling in from the person watching from far is quite different, according to relativity.
The next question is from Lawrence K. Professor, I've heard 2 lectures on the reversal of time by physics professors, not philosophy profs. Is there any support for this idea of reversing time or reversal of time in the scientific community?
It's a theoretical idea that has some traction. It's not clear that it has any practical implication in our universe. Our universe has a very strong arrow of time, and that's driven by the fact that the arrow of time conveys a passage towards higher disorder from lower disorder. And so the entropy of the universe was actually fairly low at the Big Bang, low compared to all the possible entropies it could have. And so the universe has been evolving towards higher entropy or higher disorder since the Big Bang. And so that is what gives the arrow of time. And there would have to be an overall reversal of that trend to even imagine seeing the arrow of time reverse. So there's no physical mechanism we understand within the laws of thermodynamics whereby the time arrow could reverse. And so I think it's a theoretical idea that has no basis in observation.
The next question is from Jim Whitehead, who sent an email. Does the law of conservation of energy imply that the universe has a finite amount of energy and is therefore finite in size?
So the law of conservation of energy does apply to the universe as a whole, but it doesn't directly implicate the universe's size. So the Big Bang obviously includes the propulsive energy that leads to everything moving away from everything else. So you could think of it as kinetic energy if you like. But it also has increasing gravitational potential energy because of the gravity everything exerts on everything else. And the conservation of energy comes in because the energy for the Big Bang could have been borrowed, if you like, in a sort of accounting sense, from the vacuum of space. So you can still talk about the law of conservation of energy even when it comes to the Big Bang itself, but that law, the conservation of that law or the violation of that law does not really affect space itself. Space is driven by the constituents of it, and in this case it's dark energy that's causing the accelerating expansion.
A related question, Are You Contact asks, if the universe is considered infinite, could that mean that it has no beginning or end?
The universe could be infinite. We have a horizon that's dictated by the distance we can see since the Big Bang, 13.8 billion years. How far could light travel in that time? And that's how far we can see with the telescope. We can't get the light from further away than that. So that's a limit, and that's not a physical limit. That's just an operational viewing limit, if you like, caused by the finite speed of light. So there is no indication that the universe has a boundary beyond that. But the question of whether the universe is infinite or not is not directly related to the Big Bang model itself, which only talks about the way the space-time expands from an initial singularity.
The next question is from Sarab, who asks, hello, Professor Impey. You posted about the orbital resonances in exoplanets, only accounting for 5% of the exoplanets, I think. Mm-hmm. From where did we get this idea? Is there any possibility that we might find more, that this number could increase of resonant exoplanets?
So resonance is a phenomenon that is where planets line up in their orbits in a mathematical sense, so that the ratio of the periods of their orbits is ratios of whole numbers. That's the formal definition of resonance. Resonance is pretty rare in our solar system. None of the major planets show a resonance. A couple show near resonance. The most dramatic example of resonance in the solar system are moons of Jupiter, 3 moons of Jupiter, which are in a 4:2:1 orbital period ratio. Exoplanets have shown some striking examples of resonance, and that's because we do know many exoplanet systems. The 6,000 exoplanets known include many systems, hundreds, that have multiple planets, and so the potential to look for resonance is there. So that 5% is a pretty sturdy number because it's based on observation of hundreds of exoplanets with multiple planets in each system where we could detect resonance if it occurred. So I think the 5% is a good number. And the reason it's so low is that resonance is an unstable situation, and over time perturbations and interactions between the planets will kind of act to destroy this the particular lining up of the orbits that lead to resonance.
The next question is from Aerospike, who asks, can you explain Kerr rotating black holes, and talk a little bit about how rotating black holes are different from non-rotating black holes?
So an indication of how difficult general relativity is, for those who were wondering, I mean, it's known to be a highly mathematical and successful theory of gravity, are that when you want to solve a real physical situation using the tensor equations of general relativity, you have to generate a metric. And a metric is a mathematical description of the space-time for that physical situation. And in a goal is to have an exact solution, an exact mathematical solution, as opposed to using a computer and simulating it. And in the entire history of general relativity, 100 years, there have only been two exact mathematical solutions or metrics. One is the Schwarzschild metric, after Carl Schwarzschild, one of the founders of black hole theory early in the 20th century, and that's a non-rotating black hole. And the other is the Kerr metric, from a theorist who is from New Zealand in the 1960s for a rotating black hole. And that's it. There's only ever been those two metrics in the history of black hole theory that can be solved exactly mathematically. And the black hole rotating scenario is by far the most important one, because we think that especially collapsed objects all had angular momentum, stars that died, and so that angular momentum is conserved, and the collapsed object that's left behind will have angular momentum and be spinning. So the Kerr metric is essentially the sort of routine go-to mathematical description of most of the black holes we see in the universe.
The next question is from Ronald, who's on with us live. Is the ice found on other planets the same as the ice that forms on Earth?
So it can be ice. Ice seen on other planets or moons in the solar system can be ice, as in water ice, but it is also possibly frozen materials of other kinds. So astronomers use a slightly more general term for ices, or volatiles is another way they put it, which is a set of molecules which have a frozen form, have a solid form. For example, when you look at Mars, the shrinking and expanding Mars polar caps through its seasons are mostly frozen carbon dioxide. Now there is some water mixed in with that carbon dioxide. So those ice caps are essentially dry ice, which comes and goes. And dry ice doesn't have a liquid phase, or carbon dioxide doesn't have a liquid phase, so it goes straight from a solid to a gas. There are other possible frozen gases, such as methane or ethane, ammonia. These also could potentially be seen in colder parts of the solar system. But water ice is fairly abundant, so it is one of the most common molecules in the universe.
And the next question is from Andrew, who's on with us live. If someone took a spacecraft and flew towards the edge of the universe and could somehow outrace the expansion of the universe, where would they end up? Would they end up at the edge of the universe?
I think it's hard to tell. It's an interesting thought experiment. If you were able to outrace the expansion, which implies at some point going faster than light, which is not physical, then there's no indication you would reach an edge, because the inflationary model essentially posits that the early exponential expansion of the universe by many orders of magnitude sort of thrust a large amount of space-time beyond the horizon, or beyond the range we can see with our telescopes. And that implied if you could outrace the light that we see from the universe that tells us about the universe, you would still be in regions of space-time that were expanded early on by inflation. So you would not find an edge. Now, whether there is any edge at all, or it's just a vast universe, vastly larger than the horizon universe we see, is unclear.
The next question is from Quasi, who asks, what are the potential implications of quantum gravity theories on our understanding of the relationship between gravity and the flow of time?
The quantum gravity idea is important as far as time goes, because physicists have speculated that when you get to the level of a reconciliation of relativity and quantum theory, you may start to realize that time itself is quantized. So in classical physics, including in general relativity, we think of time as a continuous variable. It's a continuous thing, just like space-time is continuous. If time itself is quantized, that would emerge from a theory of quantum gravity. And if time is quantized, it's very unclear what the implications of that would be. It would be an entirely new paradigm for time, and very exciting, of course, which is yet another motivation for people to try and unify these two theories, general relativity and quantum mechanics.
Excellent, thank you. The next question is from Kaniz Fatima, who asks, I don't remember this from our course, but we can address it in general. But the question is, from the course, you showed that space travel is possible through, she didn't remember exactly, but she thinks it was a wormhole. So have scientists ever thought to do that?
Yes, I mean, I think at various points in the course I alluded to some of them science fictional ideas that don't violate known laws of physics. And wormholes are potentially possible. They're possible within the theory of general relativity. They're theoretical constructs that we don't have any evidence for. And so traveling through them is another layer of speculation on top of speculation. So I think these are basically science fictional ideas, and they don't have any relevance to the practical universe we live in.
Excellent, thank you. The next question is from an email. Hernan Reyes has a second question. Apparently, the James Webb Telescope has discovered a small brown dwarf star only 3 times the mass of Jupiter. So how is it that this much less massive star is being qualified as a brown dwarf with such a small mass? How did this cloud of dust and gas manage to collapse on itself in the first place when something like Jupiter really needed to form around another star?
So the gas clouds that exist in space can collapse, and they may form individual objects like stars, or they may form stars with planets around them, and they can form in all sorts of different masses. So it's certainly possible to have an isolated gas cloud that's the size of Jupiter or a little larger. It doesn't have to be part of a planetary system. The question of definition is the one that's relevant here. Astronomers classify stars as anything that's above about 8% of the mass of the sun, because that's the fusion limit for turning hydrogen into helium in the way that the sun does by a 3-stage process. The range from 80 Jupiter masses down to about 10 or 12 Jupiter masses is the brown dwarf range. Brown dwarfs are not stars like the sun, but brown dwarfs are, by their gravity, hot enough to do the first step of the 3 steps of producing helium, which is deuterium fusion. So they can take hydrogen and fuse it into deuterium. So it's a feeble amount of fusion that means the star is glowing. And so you can call a brown dwarf a star. It's just a star with a much more feeble level of power output. And below about 10 or 12 times Jupiter mass, the temperature is not hot enough for deuterium fusion. And at that point, it's just a hot cloud of gas. And it will cool slowly over time. So something 3 Jupiter masses, as in this case, is not a star. It's not a brown dwarf. There's no fusion going on of any kind. And it's just a hot cloud of gas, hot because it has a lot of internal pressure and perhaps it's still collapsing.
Thank you. The next question is from Faisal, who asks, when the strongest solar winds sweep across the Earth, does connectivity to the internet and satellites temporarily stop, or does it continue?
Solar wind is a fairly steady phenomenon, so the sun is continuously emitting high energy particles and radiation, and that solar wind interacts with the magnetic field of the Earth. The magnetic field of the Earth, of course, is a sheltering and shielding effect, which benefits us greatly because it stops high energy particles causing mutations on the Earth's surface, and it stops them massively disrupting telecommunications. So we only see the impact of the solar wind or solar storms on telecommunications when the sun is in an active phase. The sun right now is in an inactive phase, a sunspot minimum, but when it goes to the maximum, then we will see interferences with telecommunications. And then when there's special and rare storms, like a super flare, which happens every century or millennium, then you could have a wholesale destruction, really, of telecommunication satellites and their delicate electronics.
The question, next question is from Neha, who's on with us live. How can radio astronomy be useful in the search for extraterrestrial life?
Well, radio astronomy can really help find microbial life, which we imagine to be the most common form of life beyond the Earth, since all the ingredients for life exist on many planets, and on Earth there was life that was microbial for billions of years before it became big enough to see without a microscope. Radio astronomy is only useful for detecting artificially generated radio waves. So there are naturally occurring radio waves in the universe from synchrotron and cyclotron radiation, high energy electrons moving in magnetic fields. But in the case of looking for life, what you're looking for is intentional creation of radio waves through technology, through radio technology, through transmitters. And that's what SETI is doing, and SETI has been doing that since 1960, looking for intentionally created radio waves that are pulsed and containing information and not produced naturally and astrophysically by stars or gas. That's a standard method of SETI, and so far has not succeeded. No one has ever seen a artificially generated radio signal coming from an intelligent technological civilization. But if they exist, then it's a worthwhile thing to look for.
The next question is again from one of our live viewers. Karen would like to know, the Ingenuity helicopter won't be flying on Mars again, but it's been very successful. Do you think flying drones is a good future choice for planetary exploration?
Yes, the Ingenuity helicopter was a phenomenal success. It's a very challenging thing to develop a helicopter to operate in the 1% of Earth's thickness atmosphere of Mars. I mean, helicopters, there's not much to push on basically, and it's very hard to make it stable. It was originally intended for less than a dozen flights, and it did many dozens and was very successful before its ultimate failure. And yes, now helicopters and drones are a standard part of the toolkit of NASA as it goes into different locations. Mars for sure, but also Titan, where the Dragonfly mission involves essentially a drone technology, and the technology is much easier to do on Titan, which has an atmosphere as thick or thicker than the Earth, and so flying the drones there is very similar to flying a drone on the Earth. So anywhere where there's a decent thick atmosphere, drones and helicopters will work, and the miniaturization of their technology and their mobility and nimbleness means they can cover vastly more ground than a rover can, even though they're not as well equipped as a rover because they have to be light. So their instrumentation is limited to simple chemical sensing and a camera. But I think they're going to be part of almost every outer solar system mission that lands on a planetary surface.
Bryce is on with us live and would like to know, would a pilot who is constantly traveling at higher altitudes and speeds, presumably, be susceptible to time dilation and age differently?
In principle, yes. Gravity is weaker in gravity in a weaker field of gravity, time moves faster. So time slows down in stronger gravity. So as you fly around, you are getting slight time dilation compared to what you would experience on the Earth. But this effect, which was measured with atomic clocks in the 1950s, one of which was flowing in a high-altitude spy plane and the other which was on the Earth's surface, corresponds to, over days of flying, a nanosecond difference in the clocks. So there's no way physiologically a human would recognize such a tiny time dilation.
The next question is from Omar Abdi, who asks, is the universe expanding, and can you tell me how fast it is expanding?
Yes, the universe is expanding, and that was measured first by Edwin Hubble in the late 1920s using telescopes at Mount Wilson Observatory in California. And the speed of the expansion in the present day and in the nearby universe is measured by something called the Hubble constant, which is named after Edwin Hubble, of course. And the Hubble constant comes in at around 70 kilometers per second per megaparsec. And so if you unpack what that unit is, it means that for every megaparsec in distance from the Earth, megaparsec is 3.3 million light years, the speed of recession or expansion is 70 kilometers per second. So if you go 10 megaparsecs, the expansion or recession speed is 700 kilometers per second, and it goes linearly like that. So the Hubble constant, this number, expresses the amount of the current expansion.
Excellent. It is 10:58, so we will probably have time for one final question, and then we'll be wrapping up for today. Since we have 2 minutes, we'll do a big one. Aditya asks, Elon wants to terraform Mars. Neil Tyson said we should protect and fix our Earth as it is more resource efficient. What are your views?
Well, I'm with Neil deGrasse Tyson on this one because it is far cheaper and better for us to solve the problems of the Earth than to go to Mars. It's not a question of terraforming Mars. Elon Musk is correct that the technology does exist to terraform Mars. NASA has had design or planned studies of this, conceptual studies of this for decades. But it's a phenomenal undertaking, phenomenally expensive and phenomenally time-consuming. It could never be done in less than a few centuries, and for costs of an indeterminate cost, but tens of trillions of dollars. So terraforming Mars is a phenomenal undertaking to allow humans to live anywhere on Mars rather than just small little habitats that we build. And then the question of how would we all get to Mars, or any significant number of people, is unsolved, and even Elon Musk's Starship will not solve this problem. It may get hundreds and eventually thousands of people to Mars, but in any reasonable timescale, it won't solve the problem. So we are far better off solving the problems of the Earth than considering terraforming Mars. It's a visionary idea that has some validity physically. It's possible, but it's simply not a smart move at the present time. Thanks for that last question, and for all the variety of the questions so far this week, and to Matthew for facilitating. And I don't remember if we have another one on the books, but we'll be back in a few weeks.
We do. I'm going to check right now. Our next one is February 28th. We will see everyone on February 28th. If you are not subscribed to our channel, make sure you like and subscribe to our YouTube channel. You'll get those notifications. And then if you scroll up to the top of the chat, there are links up there so that if you'd like to get on our mailing list, you can join a mailing list or Google mailing list. And there's also a calendar link up there for a Google Calendar. So if people would like that, that's another way to find out about our upcoming live sessions. You'll hear from us again in just a couple of weeks, and I'll see you all later. We hope you have a good rest of your Valentine's Day and a good rest of your week. Take care, everyone.